Hello, my name's Kevin. I'm a professor of pure mathematics at Imperial College London, and I'm extremely grateful to be asked to give this talk. I looked at who's given these talks in the past, and it was quite a collection of luminaries, so I was rather surprised to be appended to them, but there we go. And also that I love speaking to undergraduates. They've become, perhaps surprisingly, sort of an integral part of my research over the last few years. And so thank you very much to the LMS and ICMS for this invitation. You were told that you could put stuff in the chat during the talk, but I probably won't be looking at the chat during the talk, just to warn you, although I certainly will be around for questions afterwards. So what's this talk about? I'm going to talk about two sort of recent developments in getting computers to do mathematics. I'm going to talk about something called large language models. I should say you don't need to be an expert in any of this stuff to follow the talk. The talk's been designed for undergraduate mathematicians. So I'll talk about the strengths and weaknesses of large language models when it comes to mathematics, and the strengths and weaknesses of interactive theorem provers when it comes to mathematics. I'll show you what both of those things are, and I'll show you what they do, and we can compare and contrast them. And then the main body of the talk is just talking about where we are, what the state of the art is, and where we're going in this area. And then after that, I'll say something about, I hear that some of you are interested in doing PhDs, so I thought I would talk a little bit about what it's like to do research in the area that I work in, the area of interactive theorem provers. So let's go. How do computers work in mathematics? So in the old days, computers were used by mathematicians to compute, so to do tedious calculations that humans didn't want to do or didn't have time to do themselves. And computing can give you evidence towards a conjecture. That was one of the major uses of it originally, like the Birch-Swinnerton-Dyer conjecture. This initially came about after a lot of computational experiments that gave us some kind of understanding as to what was going on. But here's an even simpler example, Goldbach's conjecture. It says that every even number, 4 or more, is the sum of 2 prime numbers. So 4 is 2 plus 2, 6 is 3 plus 3, etc., etc. So this is an open problem. But one thing you can do is you can attempt to verify the Goldbach conjecture, to see if it's actually a reasonable conjecture, see if it's a reasonable guess. We can try and check it for all even numbers up to some bound, and indeed the current record is 4 times 10 to the 18. Every even number between 4 and 4 times 10 to the 18 is the sum of 2 prime numbers. And of course, the problem with this approach, checking lots and lots of examples, it gives you evidence in some sense that the conjecture is true, but you're never going to prove the Goldbach conjecture that way, because we've got all the way up to 4 times 10 to the 18, and so we're 0% of the way there, because there's still infinitely many even numbers left. So let me not talk about the Goldbach conjecture right now because it's too difficult. Let's take a much simpler problem just to indicate. I want to show you various ways of attacking this problem. Let's try and prove there's infinitely many prime numbers. And so how would one do that? I mean, if we want to use a computer, we could use a Python program. We could knock off some Python code, which starts printing out prime numbers. And there we go. It's my daughter calling me up. We could write a Python program which starts printing out prime numbers, and we could observe that Python program doesn't seem to stop. And so then we could go and have our dinner, and we could come back and it still hasn't stopped. And then we could go to bed and get up the next morning, and this Python program is still printing out prime numbers. And this is evidence that there's infinitely many prime numbers. But of course, although Python can be used to compute, we can't use it to reason. So we can't expect it to come up with Euclid's proof that there's infinitely many prime numbers. That's not what Python does. But Python is not the only way that we can use computers nowadays, sort of traditional programming languages. And the point of my talk really is just to demonstrate that we can use computers in new ways. And indeed, we can use computers to prove that there's infinitely many prime numbers. And I'm going to show you two ways of doing it. The first way, let's use a large language model. So that's something like ChatGPT, something that probably most of you have heard of. Let's use ChatGPT to prove there's infinitely many prime numbers. So let's go over here. Let's try new chat. There we go. So you never quite know what you're going to get with ChatGPT. It might be super slow or it might not even work. But let's have a go anyway. Prove that there are infinitely many prime numbers. There we go. Something went wrong, you see. So rotten luck. So fortunately, I was prepared for this. And here's one I did earlier. Hard luck. Here's what I did earlier. This is what it printed out yesterday when I was preparing the talk. And it's slowly but surely, it was very pleasant to watch it appearing. I'm sorry you just didn't get the joy of seeing that. This is Euclid's proof that there's infinitely many prime numbers. It was interesting that it actually it's written the proof in LaTeX, which I thought was quite interesting. I tried it again and didn't write it in LaTeX. It's put dollar signs around all of the mathematics, and you can see that this is, this at first glance, this looks exactly like Euclid's proof. If you read it very carefully, you can see that somehow it's not quite right, but it's kind of like an eta. If n is composite, there exists a prime factor p of n. Since p is a prime factor of n, it must divide the product of p1 up to pn because it divides the product of these numbers plus 1. That's sort of nonsense, but it's sort of mostly right. And if you're reading it quickly because you've got a lot of scripts to mark, you might give it 10 out of 10. So there's quite a good effort at proving that there's infinitely many prime numbers. Certainly, it's the right technique, it's the right strategy. So there you go. There's large language models. And now let's use an interactive theorem prover. So there's let me show you a completely different way of showing you that there's infinitely many prime numbers. And fortunately, my interactive theorem prover is more reliable than my large language model, apparently. So let's write down the statement. There's lots of ways that we can say there's infinitely many prime numbers. Let's say for all natural numbers n, there exists. I mean, this is the easiest way of saying it. There exists a prime. There exists a p such that p is bigger than n and p is prime. So there we go. I've got some import. This import here imports the theory of prime numbers. This interactive theorem prover, it knows the axioms of mathematics, but it doesn't actually know any mathematics until you start importing stuff from its library. This is an import from the theorem prover's mathematics library that contains the definition of a prime number. And there we go. And so now we can play an exciting computer game where the goal of the game is to prove this statement on the right here, which is the statement that there are arbitrarily large prime numbers. And I could go through the proof, but I'm not going to go through the proof. I'm going to type in the library search tactic. This is quite a powerful tactic. There we go. The library search tactic has succeeded, and it's suggested. It says try this. If we click here, there, then we can tell. So apparently, according to the interactive theorem prover, our goals are now accomplished, which means we've proved there's infinitely many prime numbers. And the way we've done it is we found the result in Lean's mathematics library already. And it was called nat.exists infinite primes. So there's two ways of using a computer to prove that there are infinitely many prime numbers. That was Lean, my favorite interactive theorem prover. So what just happened? Of course, did the computer figure out what was going on all by itself? Well, no, in neither case did that happen. With the ChatGPT version, what's going on is lots and lots of proofs that there's infinitely many prime numbers on the internet, and most of those proofs are Euclid's proof, written down by lots and lots of humans. And ChatGPT, this large language model, has been trained on the internet, and as a consequence, it's seen lots of proof that there's infinitely many prime numbers, and it's seen enough of them to realize that it can kind of like mix them up together and come up with its own proof somehow. It knows something about the way that the words are strung together to be able to construct its own essentially accurate but not quite accurate proof that there's infinitely many prime numbers. So in some sense, because the internet is mostly written by humans, what it was doing really was just following a human proof. So what did the lean proof do? Well, the lean proof invoked a tactic, and the tactic was library search, which searched through Lean's mathematics library for the proof. And if we go back to Lean, we can right-click on this proof, and here we can see the proof in all its glory. This is the proof. This is the proof that was invoked. You see, this is a proof in the data.nat.prime file. The file that I imported contained this proof. And you can see that it's not quite Euclid's proof, but it's a minor variant of Euclid's proof. How does it do it? It's got a formula for P. P is min fac of n factorial plus 1. Remember, n is given, and we're trying to find a prime number P, which is at least n. And so P is min fac of n factorial plus 1. If we hover over min fac, we see that nat.min fac returns the smallest prime factor of the input natural number n, as long as it's not 1. And so the next thing we do is we prove that n factorial plus 1 isn't 1, and then we're guaranteed that this is the smallest prime factorial, smallest prime factor of n factorial plus 1. So here's the proof that it's prime, and here's the proof that it's at least n, and the proof is by contradiction. You can see what's going on if I click, probably if I click here, yeah, there we go. If I click here, we can see on the right, we can see the current state of Lean's brain. We're trying to prove that if n is at least p, then we have a contradiction. P is defined to be the smallest prime factor of n factorial plus 1. And the contradiction is that first we prove that p divides n factorial, because it's smaller than n, so it certainly divides n factorial. N factorial is the product of a bunch of numbers, one of which is p. And because it divides n factorial, and it divides n factorial plus 1, it divides 1. And if a prime divides 1, then, I mean, that can't happen. And so there's the contradiction that we were seeking, and that's the end of the proof. So where did this proof come from? This proof was typed in by a human. In fact, you can click on, we click on various things, we can see, well, anyway, we can see Scott Morrison 5 years ago put this proof into Lean's mathematics library. So at the end of the day, I was saying, oh, the computers have proved there's infinitely many prime numbers, but at the end of the day, if you trace back what's going on, the source of the proof was really a human. So maybe I could be a bit more precise. What's happened is that a human has taken the standard proof and has translated it from human language into this computer code here, which is a programming language which is sufficiently expressive that it could represent a mathematical argument. So at no point is the machine actually doing any thinking, right? And at no point has this thing become autonomous and it's thinking by itself in neither system. But at the end of the day, you can argue that in some way a computer proved that there were infinitely many primes, in the sense that someone else could come along who didn't do that work themselves and get the computer to do it. Okay, what's next? Let's do a harder question. Let's prove there's infinitely many primes which end in 7. So this is a harder problem. And in fact, this is, you can prove, when I was an undergraduate, I saw in my basic number theory course, I saw, for example, a proof that there were infinitely many primes which were 1 mod 4, and a proof that there were infinitely many primes which were 3 mod 4, using sort of tricks. It's sort of modifications of Euclid's argument. But infinitely many primes which are 7 mod 10, this is deeper. So it's certainly true that there's infinitely many primes which are 7 mod 10, because 7 and 10 are co-prime, and it's an old theorem of Dirichlet that if A and B are co-prime, then there's infinitely many primes congruent to A mod B. So we can invoke Dirichlet's theorem. That would be good. But is there a trick way of doing it without having to invoke sort of a more a sort of a sledgehammer-like approach, because here, to prove Dirichley's theorem, you need to set up a lot of machinery, some theory of sort of Dirichlet L functions and things like this. So I don't know of an approach which avoids that. And the problem with Euclid's strategy is that you've got lots of primes that end in 7. You can multiply them all together and then do something to make the product end in 7. You're like, I don't know, multiply it by 10 and add 7 or something. And then you've got a large number that ends in 7, which isn't one of the primes that you've come up with. And if it's prime, then that's great. But if it's not prime, it's a large number which ends in 7. But unfortunately, it can be the product of a prime ending in 3 and a prime ending in 9. And so you don't get, you need some kind of algorithm that comes up with a new prime that ends in 7. And Euclid's approach does not give you such an algorithm. So that's the reason that the elementary proof fails. So we could go back to the large language model and ask it to prove that there's infinitely many primes that end in 7. Is there any point doing it? Let's try. New chat, is this going to work? Prove that. I don't know why I'm wasting my time. Prove that there are infinitely many primes which end in 7. Yeah, so there you go. Server's overloaded right now, but fortunately, I was prepared for this, and that's what we get. And the prover confidently announces that it can prove there's infinitely many primes which end in 7, and then you read it, and there's just, you can see what it's done. It's done the kind of thing that an undergraduate would do, right? The undergraduate's seen the proof that there's infinitely many primes, and it decides to mimic the proof. They decide to mimic the proof. And so here we go, like, here's the hard bit. N's got a prime factor. If n is prime, then we're done. If n isn't prime, then we have to try and do something. And so the mistake is going to be somewhere in this paragraph. And indeed, it's a ridiculous mistake. What do they say? They say any prime greater than 5 must end in either 1, 3, 7, or 9. That's a true statement, and cannot end in 7. That's a load of old nonsense. So in fact, that's the assertion that there are no primes which end in 7. And so therefore, n doesn't have a prime factor that doesn't end in 7, which means that n must be prime. So, make of that what you will. It's talking twaddle, unfortunately. And so you can kind of see that we've reached the limitations of the system now. So yeah, very wrong. And as I say, it's the kind of thing, if you're like me and you've spent 30 years marking undergraduate scripts, and that's the kind of thing that you're sort of expected, that you expect from some undergraduates who are just sort of optimistically trying to mimic what they've seen already, but they're not really engaging their brain, some of them, so they might, or they're trying to get it past you. So there you go. It feels like something an undergraduate could write, and that's exactly not surprising, because ChatGPT is trained on the internet, and the internet is written mostly by humans. So what about the interactive theorem prover? Well, that's a different kettle of fish. So it turns out that actually Lean can prove that there's infinitely many primes that end in 7. I won't show you the complete proof. I'll show you part of the proof. Part of the proof, it looks like that. In fact, why don't I show you? There's no reason. Let me just switch over to, there we go. Look, here's part of, this is great. Look at this. This is maths. This is what maths looks like, apparently. So, there was a theorem. There you go. Theorem DVEF says that Wekek that, and V11 is that, and V30 is that. And you might, this proof is as a valid Lean proof, but you might realize that it looks a little bit different to the Lean proof we were looking at earlier. And the reason it looks very different to the Lean proof we were looking at earlier is because it was not written by a human. It was written by a computer. So you kind of think, oh, this is great. Computers can prove that there's infinitely many prime numbers that end in 7. But unfortunately, this gigantic, completely incomprehensible proof of Dirichley's theorem was not really, it was written by a computer in some sense, but the computer actually translated the proof, which was originally written in another interactive theorem prover called MetaMath. And the MetaMath proof was written by a human. So there was still a human at the end of it. And this human is Mario Carnero. He wrote the MetaMath proof. It's the elementary Erdős-Selberg proof of I mean, it comes out of the prime number theorem. It's the same sort of thing. So if you know enough about L functions, you can prove Dirichlet's theorem. So Mario Carnero wrote the MetaMath proof, and Mario Carnero also wrote the program which did the translation. Mario's good at computers, and it was translated into this incomprehensible, to me at least, Lean proof. But at the end of the day, you can run it, and Lean says it's correct, and so it must be correct. So there you go. So now let's do a thought experiment. Let's instead ask ourselves, can we get a computer to prove something like the Birch-Swinnerton-Dyer conjecture? You know, a harder problem. This is one of the clay millennium problems. It's some statement about elliptic curves. And okay, that's sort of a reasonable question. Well, the technique I showed you, library search, let's look through Lean's maths library. Unfortunately, Lean's maths library does not contain a proof of this unsolved conjecture. And the reason is that nobody knows a proof. And the large language model, well, you know, some computer scientists think that it's only a matter of time, but I'm slightly skeptical about that assertion. I don't think that the plan that we have for large language models right now is going to be good enough to prove things like the Birch-Swinnerton-Dyer conjecture, because right now it's sort of learned, it might have learned the internet, but there's not a proof of the Birch-Swinnerton-Dyer conjecture on the internet. And are there enough ideas on the internet that you could put together to prove the Birch-Swinnerton-Dyer conjecture? I mean, if that was true, I'm not entirely convinced that it's going to be ChatGPT that can do that. I mean, who knows what the future will hold, but right now I'm not seeing any evidence that that's going to happen. So what have we seen so far? We've seen large language models and interactive theorem provers doing very well at mathematics, which is kind of the kind of mathematics which 17-year-olds are doing. Sort of end, A-level school, early undergraduate, possibly 18-year-old mathematics level. And then beyond that, the problems start to arise. The large language models, they can generate proofs by themselves, but they start confidently talking nonsense. They'll happily prove that there's infinitely many primes that end in 7 by just mimicking something they've seen. They mimic it, unfortunately, in a situation where the techniques they have can't be made to apply. And the theorem provers, they're super accurate, but they need, at the end of the day, they need to have a human taking on a major project to type in stuff. And typing in proofs into a theorem prover is slow going. It's sort of slower than writing them down on a piece of paper, because interactive theorem provers, it turns out they're quite pedantic. Interestingly, the weakness of each system is a strength of the other system. We've got humans powering the libraries that the interactive theorem provers are using. But the large language models are very good at writing stuff by themselves. So on the other hand, that large language models are very good at also making mistakes. But you can't make a mistake in a theorem prover. The theorem prover just picks up on the mistake instantly and gives you the feedback saying, no, you can't do that. So you can imagine that the systems somehow complement each other. So if each of the systems have weaknesses which are fixed by the other system, then let's put them together, right? That's the next step. And then maybe we'll make some, mechanical math monster or something. So, of course, people are trying to do this, and this can be done. And I'll show you an example of what happens when you do it. And here is something that I found sort of astonishing, I guess, when I first saw it. What we have here is a Lean proof. And this is a Lean proof of half of an old IMO problem, part B of I think it was part B of question 2 on the 1964 IMO, as I recall. And it says, prove that if n is a natural number, then 2 to the n plus 1 is never a multiple of 7. So the older IMOs, that's far too easy to be a current IMO problem, but the old IMOs, the standard was far more varied. So that is certainly the kind of question that you could put in front of a first-year undergraduate now. It's not an unreasonable question. You can prove it by induction if you're careful. What's happened here is that the question was given to a large language model, and the large language model was asked to write lean code that corresponded to the proof, and it managed to do so. I mean, it took a while to do so, like original efforts were incorrect, and then you get some feedback from the theorem prover saying, no, this is wrong. Can you try and fiddle with your output? And after some back and forth, but there was no human involved. The computer did it all by itself. It's come up with a proof, and as you can see, so it applies induction on line 6, and then it applies it again on line 7, and then actually again on line 10 and line 12, if you like, and then one more time for good measure on line 16. So this is this is sort of a proof. It's sort of all over the place in some sense, this proof. But at the end of the day, it does compile. I could translate it into human language for you, but I won't do it. For example, the first line says it suffices to prove that 2 to the n plus 1 is never 0 mod 7. That devud if mod x 0 is the lemma that if A divides B if and only if B is congruent to 0 mod A. And so then, this next line is about 2 to the n plus 1 mod 7 is 2 to the n mod 7 add 1 mod 7. Things like this. It is possible, if you know Lean's language, it is possible to actually read what's going on here. The easiest thing to do, of course, is just cut and paste it into Lean itself and then just watch it happening. So that's kind of great. That's a large language model writing computer code. And so that was at Facebook's large language model. It wasn't ChatGPT. But at the end of the day, it has solved part of an old IMO problem. So you're kind of thinking, great, that's the future. But actually, when you think about it, where are we here? We're still at sort of the same place, right? School stroke early undergraduate level. That's where we are. And, it's a start, right? It's something that the AI people are extremely excited about because they've seen exponential growth in the last few years. So they're extremely excited. And I think the mistake that some of them are making is assuming that exponential growth is just going to continue. And in 5 years' time, they're going to be solving the Birchland-Swinnerton conjecture. I think that's a very easy mistake to make. But on the other hand, maybe I'm making the mistake. I guess, we'll find out. We'll find out soon enough. So, of course, the dream is that one day you're going to type the Birchland-Swinnerton conjecture into a machine and you press a button and it solves it. But right now, it's science fiction, right? It's not a dream. It's just a fantasy. It's complete science fiction. And an example, one of the many reasons why this is science fiction, is that actually it's extremely difficult to even state the Birchland-Swinnerton conjecture. And the reason it's very difficult to state it is the Birchland-Swinnerton conjecture. What's it about? It's about elliptic curves, and in particular, it's about the L function of an elliptic curve over Q, and it's about the behavior of that L function near the point S equals 1. But unfortunately, the power series, the infinite sum that one uses to define the L function of that elliptic curve only converges for the real part of S bigger than 1.5. And then, just like the Riemann hypothesis, right, only works for real S bigger than 1, and then you have to extend. So extending that L function from real part of S is 1.5 to real part of S is 1, you need all of the machinery that Wiles and Taylor developed in the 1990s to prove Fermat's last theorem. And of course, the system, no system has this right now. No large language model understands that proof, and no interactive theorem prover understands that proof. So, at the end of the day, I haven't shown you any evidence because I haven't seen any evidence that large language models, I've seen them having what look like ideas in some sense, but I haven't seen them having sort of mathematical ideas, and I certainly haven't seen them having important mathematical ideas. I've seen them sort of going wrong when presented with the opportunity to have an important mathematical idea. And interactive theorem provers can certainly understand modern mathematical ideas, but they need to be taught by a human who already knows them. And so from what I've said so far, you might kind of guess that we're sort of stuck at school level mathematics, because sort of the vast majority of the successes I've pointed out have been that kind of level of mathematics. But actually, that's not the case. We have seen some spectacular examples of computers engaging and helping at a much higher level. So the next part of my talk, I'm going to give you some examples of how computers have been engaging with modern mathematical research. So the very beginning, as far as I was concerned, I learnt the language of the lean theorem prover. I knew what a scheme was because they show up in my work. And I was running a lean club for undergraduates, and undergraduates wanted a project. And so I came up with this project of teaching lean what a scheme was. And so me and a bunch of undergraduates started working on this. We had a glimpse of that slightly earlier. Look, we ended up with the publication, Schemes in Lean, published in Experimental Mathematics last year. So this was me. Scott Morrison is another lecturer. And then these four other people were all undergraduates at the time. 3 of them were first year undergraduates. We ended up with a publication. That was quite good fun. And I was quite excited when we got all this working, started running around the department telling algebraic geometers that I'll taught a computer what a scheme was. But the algebraic geometers were less impressed because they were saying, well, I knew what a scheme was when I was a PhD student. So I realized we had to aim higher. And so the next project I came up with was that Peter Scholzer in 2018 got a Fields Medal for something called perfectoid spaces. That was kind of a cool sounding thing. And most people in my department don't know what a perfectoid space is because it's a very technical thing. But perfectoid spaces are used in the area of mathematics I work in. I mean, they're used in lots of areas now. They've been used in commutative algebra and in the Langlands program, which is where I work. And so I'd learned what a perfectoid space was. And so me and a couple of people I met on the Lean chat, we defined perfectoid spaces in Lean. And then I went around telling the algebraic geometers, and this time they were much more impressed because none of them had a clue what a perfectoid space was. That was the plan. So there we go. We got a paper out of that as well, published in a computer science journal. You can tell that because it's sort of double 2 columns. That's the giveaway. But we had to go with their funny ideas about what a paper looked like. But at the end of the day, the reason we did this was to raise awareness of the area. I mean, it was to see if Lean could handle the complicated definition like perfectoid space. But it was also, had it worked, and it did work, we could go around saying, look what we can do. Interactive theorem provers can do perfectoid spaces. And a lot of people got kind of excited about this, which was nice. There was some media attention, which was unexpected. And we made a nice web page. If you get your hands on the slides afterwards, you can see our little web page. But the main thing that happened, which was the thing I really wanted to happen, was a bunch of sort of PhD students and postdocs. They all showed up in the Lean chat room, the Lean Zulip chat, and the area began to grow. So I should say Zulip is something like Slack, if you've ever used Slack or Discord. I mean, it has a lot of similarities to them, but it's different. Let me just show you the Lean Zulip chat. This is sort of an amazing thing. It's extremely active chat. You see, well, I mean, somehow since this talk started, there's 25 people bickering about names of things in the set theory module. There's what am I looking at now? Oh, here we go. There's a pedantic argument about whether the zero algebra is a normed ring, because one of the axioms for a normed ring used to say that the norm of 1 was 1, but in the zero algebra, the 1 is equal to 0, so the norm of 1 is 0. And so there was a discussion about changing the axiom to the norm of 1 is less than or equal to 1. There's Johan Kommerlein, he's my co-author. Some very smart. There's Reed Barton, who went to the IMO 4 times or something. you can sort of see various people online here. Daniel Selsom is an expert in AI. Matt Ballard's a lecturer at USC. I mean, there's people around, from undergraduates to sort of professors. It's an amazing place. So let me get back to the mathematics. Sorry about that distraction. The catch was in our work, the reason you could tell it was a publicity stunt was that we didn't actually prove any hard theorems about perfectoid spaces. What we actually did was just sort of got to the definition and then we stopped. And it was the theorems which were the meat in some sense. It was the theorems which were on Schultz and the Fields medal. And so in some sense, the work was rather shallow. But in 2020, Schultz had challenged the formal prover community. Schultz, of course, noticed that we had made perfectoid spaces. And he said, okay, then why don't you prove a hard theorem in your systems? Can the theorems do that? Not just make a hard definition, but prove a hard theorem. So he came up with an explicit question, and he wrote a blog post about it on my blog, because I've been blogging about this for a few years. But basically, Schultz proved a technical result, and it was sort of nearly 10 pages of sort of messy calculations. And he'd gone around asking people if they'd read those 10 pages carefully, and everyone had said no. But the technical result was somehow underpinning the entire theory, proving that there were sort of no non-trivial extensions between liquid vector spaces. And Schultz wanted to know that this theorem was true. Somehow, if this theorem wasn't true, then everything was going to fall apart. And so now this was a genuine challenge, because we were going to have to prove we were going to have to make a lot of things. We were going to have to teach lean, or whichever theorem prover we use lean. We were going to have to teach a theorem prover a lot about homological algebra and a lot about these condensed sets, these new things. Abelian categories and Grothendieck topologies have been around since the 60s, but condensed sets were very new. The proof originally used stable homotopy groups of spheres, so that's something coming from topology. And there was also, there was a whole bunch of other things. There was a lot of commutative algebra and sort of machinery needed. Theorems about finitely generated monoids, various bits and bobs. But because the lean community had rapidly expanded in the last few years, we had the staff to do this. And it was a big open source collaboration. Anyone who wanted to join in could join in. We had like a PhD student from Cambridge, Bhavik Mehta, who knew a bunch of stuff about topologies on categories, and he formalized that stuff. He just made that contribution and then went back and did other things. That was very appreciated. So we got going. There was some momentum behind the project. We proved an intermediate result. Schultz got very excited. And we got a piece in Nature written about the project, which was quite surprising to me. You don't often see pure maths in Nature. We finished the project in July 2022. Those were the leaders of the project, Komalan and Topaz, two young mathematicians, two young arithmetic geometers. I played a part, but I didn't run this project. I did some of the work, but these people did a lot more. And one of the exciting things was we didn't have to do the theory of stable homotopy groups of spheres, because as part of the analysis and typing it into the theorem prover and thinking about the correct way to do things, Komalin found a new argument which managed to avoid having to generate the theory of stable homotopy groups of spheres. So that was quite exciting. So we came up with a simplification of the argument. And it was all done completely publicly in this sort of open source way that I found very exciting. So what about my co-author Masso, the other person involved in the Perfectoid project? He turned to differential topology, and he proved the following theorem. Let me show you this. He proved the following theorem, that you could turn a sphere. Ooh, let's turn that off. He proved that you could turn a sphere inside out. There you go. There's a nice low quality video of a sphere turning inside out. So what's happening? The sphere is allowed to pass through itself, but it's not allowed to sort of crease or snap. And that's the idea. And it's not at all obvious that you can do it. And when you see that proof there, and then you kind of think, well, how the heck are you going to translate that into a theorem prover? That sounds like quite a challenging problem. and it did take a couple of years for them to solve it. But in the end, they did it. They formalized an instance of Gromov's H principle. So they formalized a modern proof and deduced that you could turn spheres inside out as a corollary. So that was kind of wild. And so there's where we are with lean. And now let me talk about where we are with AI, these other techniques. So I'm going to move away from large language models now because we've seen their limitations, but AI is making other inroads into research level mathematics. Research spelt wrong there, sorry about that. So let me give you some examples. I'll give you 3 examples. First example is some researchers from DeepMind collaborated with knot theorists in Oxford, and they proved a new theorem in knot theory, where the computer and the human collaborated with each other. There's the paper there. So Davies and Tomasev, they're computer scientists working at DeepMind, and Juhasz and Lackenby, they're mathematicians at Oxford. And what they did was that they examined large tables of knots and invariance of knots. So that invariance of knots come in 2 flavors. There are sort of discrete combinatorial invariance, whose values are sort of integers or polynomials or something. And then there are continuous invariants coming from the hyperbolic side of the story, which are sort of real numbers. And the topologists raised the question that if you could predict discrete invariance from continuous invariance, that would be sort of an interesting link. And so this is specifically what the network tried to do. It tried to figure out how to work out some of the discrete invariance from the continuous invariance. And after a while, they started focusing on the signature of a knot. So that's an integer. And can they predict it from various things, such as the volume of the 3 manifold attached to the knot? And so that what they got was they got a neural network to do. This is sort of if you've been to any sort of proofs about how do generic neural networks work, this is just sort of experimental linear algebra somehow. You have these neurons and these hidden layers and this funny function that is f of x is x if x is positive and 0 if x is negative. And so they gave the problem to a neural network. They gave it lots and lots of data. And it turned out that the knot was able to learn how to predict the signature. Sorry, the neural network could predict the signature given these real number invariants with high accuracy. So after some experimentation, then you analyze what the network's doing, and it tells you which geometric invariance it's using. It can't explain what the algorithm is, but it can say which of the geometric invariants feel like they're the most important. And then the humans go away and think about these geometric invariants and how they could possibly be related to the signature. And they came up with some kind of evidence for a linear combination between the signature of a knot and the slope of a knot. This was a geometric invariant, a new geometric invariant. It's just sort of a ratio of linear combinations of known geometric invariants. And they came up with a conjecture that related the slope and the signature. And there's the conjecture, except it's not a conjecture anymore. It's a theorem. The signature turns out to be approximately half the slope. And the error is bounded by something that only depends on the volume of the associated 3 manifold and the injectivity radius. So the humans proved that theorem. That's not computers proving it, but the computers told them where to look. And the reason the theorem's sort of interesting is because it's a non-trivial relationship between geometric invariance of a knot and algebraic invariance. So there you go. There's computers being used in a surprising new way. Here's another example. This is the same team from DeepMind, but also Geordie Williamson from the University of Sydney. Here's the combinatorial invariance conjecture. Take 2 elements of a symmetric group. So given that piece of data, you can make a sort of a slightly unwieldy graph called the Bruhat interval graph. I'll show you a picture of one in a minute. It's very easy to compute, but it's sort of a large and complicated object. And another thing you can associate is the Kasdan-Lustig polynomial, which is much harder to compute, but at the end of the day, it's just a polynomial. And the conjecture is that you don't actually need the elements of the symmetric group. The conjecture is that the Cauchy-Daniel-Lustig polynomial is somehow encoded in the Bruhat interval graph. So here's an example. The symmetric group is S8, and there's the Bruhat interval graph associated to two permutations on a set of 8 elements. And the idea is that somehow you're supposed to get from that graph to the polynomial 1 plus q squared. That's the question. And again, you can make many, many examples. You can make a large data set, and you have to try and figure out which parts of the graph are relevant. And you train your neural network. You say, here's the input, it's a graph. Here's the output, it's a Cauchy-Daniel-Lustig polynomial. Now, work out what the function is. And in some cases, the neural network would get very good at predicting this polynomial. And then you kind of look at what the neural network is doing, and you realize that the neural network is focusing on certain edges in the graph that correspond to certain extremal reflections, they're called. And so this was the clue that the human needed. And ultimately, a theorem was isolated and proved by Williamson, relating this graph to this polynomial. So last example, computers and humans working in tandem, or AI and humans working in tandem. This is constructions in combinatorics. So again, it's a construction from graph theory. So here's a conjecture. If G is a connected graph with at least 3 vertices, and then lambda 1 and mu are certain numerical invariants that you can attach to that graph, the idea is that lambda 1 plus mu is going to be at least some number that depends only on the number of vertices. So that conjecture has been around for over 10 years. And what we're going to do here is we're going to fix a natural number. We're going to fix, we're going to decide that we're going to look at graphs on some fixed. It's going to be 20. It's going to be 19. Fix n is 19, because this conjecture has been checked on big tables of graphs. But of course, there are lots of graphs on 15 vertices. And so beyond some point, you can't start checking it on every graph. So we fix a number that's sort of beyond the tables, like 19. And we tell the neural network to just do experiments, switching on edges and switching off edges, and try to lower the left-hand side, lambda 1 plus mu. You see, once we fixed n, the right-hand side is fixed. So if we want to find a counterexample to this conjecture, we need to minimize lambda 1 plus mu. So you tell the neural network to do this, and this is what it does. The first graph is totally random, and then it tries to work out whether lambda 1 plus mu goes up or down if you switch edges off, and then it switches some edges on or off, and then we get this, and then we get this. So you saw very quickly the neural network has come up with the idea that to minimize lambda 1 plus mu, then you want some kind of tree-like structure, something with very few loops in. And then a little bit later, it's like, it would also be good if we had a couple of vertices that had very high degree, lots and lots and lots of, these sort of flowers, sort of a central vertex with lots of petals coming off. And you can see that's happening here. And as it goes on, it realizes that this is somehow the key. And its final answer is this graph here. We've got two flowers joined at the root. So the neural network has sort of found by itself structure which minimizes this thing which is supposed to be big. And it turns out that this final example which it found was indeed a counterexample to the conjecture. So there's examples of artificial intelligence doing kind of amazing. These are all very recent examples, all from the last 2 years. Artificial intelligence doing really quite amazing things, sort of helping humans to do mathematics. So I'm going to wrap up now, giving you some kind of insight as to what computers are doing now. Of course, the area is moving very quickly, but there's some kind of insight as to what computers are doing now when it comes to research level mathematics. But let me tell you, let me finish by talking about what it's like to work in this area as a PhD student, because my understanding is that many of you are undergraduates and are interested in, possibly interested in doing PhDs. So let me tell you what our team looks like at Imperial. So we're not doing AI stuff. If you want to do AI things, you probably need to go to a computer science department. But we are building Lean's mathematics library. So we're teaching a computer or interactive proof system, the definitions of important objects in modern number theory. So my students go to courses that are running in the mathematics department and learn basic, number theory and learn what's going on in number theory. They go to the number theory seminar and things like this. They understand what's happening in their areas of interest, and then they take parts of what's going on and they teach these things to Lean. So here's some examples. My student Ashwini, she taught Lean about p-adic L functions. Those are kind of a big thing now. P-adic L functions for elliptic curves. Maybe they're going to be used to prove the Birchton-Swinnerton-Dyer conjecture. So she taught Lean about p-adic L functions and proved a theorem. She proved the main theorem in the abelian case. Well, I guess an important theorem in the abelian case is that the values of p-adic L functions at negative integers are related to generalized Bernoulli numbers, just like classical L functions, like the Riemann zeta function. Its values at negative integers is also related to Bernoulli numbers. So David, he proved the group law on an elliptic curves associative, and he's well on the way to proving that the rational points are finally generated. Amelia, she's defined group cohomology and Galois cohomology very recently, and has proved some basic theorems in that area. So this is the first cohomology theory that we have, this first working cohomology theory. So we're building algebraic geometry slowly, but et al. Cohomology would certainly be another natural target for her. Oliver, my postdoc, he's defined Lie algebras, and he's currently working on the classification of semi-simple Lie algebras. We need this kind of thing for the Langlands philosophy. I want to teach the computer, the statements of the Langlands philosophy, so we need things like universal enveloping algebras of Lie algebras. So he's working on, undergraduate level Lie theory, if you like, but it's going great. Maria Ines, she's actually no longer my postdoc. The money ran out in January, and she's gone. She's been snatched up by Madrid and is now giving a Lean course in Madrid. When she was in London, she defined basic number theoretic invariance of global fields, the Adels and the Idels. Defined the Idel class group, proved the relationship between that and the classical class group, and she started stating results in global class field theory, which we're going to need later on. She also began to do p-adic Hodge theory. She defined the p-adic period ring B Hodge Tate, and is now working on even more profound period rings like B de Rham and B Chris. And Jujian, he's defined projective schemes. We have schemes, we had affine schemes for a long time. He's now got projective schemes working, and he's now wants to start working on sheaves of modules over these things. So he's currently doing some commutative algebra basics to make that happen. So are these people doing research? That's sort of a funny question, right? And because they're not proving new theorems, right? 10 years ago, if you worked with me, your output, you would be expected to prove a new theorem. But nowadays, you're not expected to prove a new theorem. You're expected to be formalizing mathematics that nobody ever formalized before, because this turns out this comes with its own problems. And I should actually say that David was involved. His proof of associativity of elliptic curves does seem to be novel. It was a collaboration with Junyan Su, and they've come up with a proof of associativity of the group law, which works in characteristic 2 and which does seem to be new. So in some sense, they are proving new theorems, but they're doing this because they're trying to understand at a conceptual level what's happening with well-understood theorems. So somehow a better way to summarize what they're doing is they're discovering the right way to think about theorems. And another example is Oliver's work. He proved Engel's theorem, and he was sort of unhappy with the way it was presented in the literature, and then he found some abstraction and named it an Engelian Lie algebra. And he proved that Lie algebra was Engelian. Engelian Lie algebra satisfied Engels. He reformulated Engel's theorem in a completely new way. But at the end of the day, even though they're having insights which clarify the nature parts of mathematics. What we're really doing is we're building a gigantic digitized database of modern mathematics. And this is the kind of database that I'm hoping that large language models will learn to read to stop them making errors. So somehow this is the crucial thing, because computers find it very difficult to read human literature, to read human papers, because humans are vague somehow, whereas they can certainly read computer code because somehow it follows a very precise logic. So I do believe that people are going to find all sorts of uses for this sort of technology in the future, and I'm not quite in a position to predict what those uses are going to be, but you know, is some sort of maybe, you know, AI experts are working on translating human language into Lean. This is sort of an interesting question. Translating proofs is hard, but translating statements, they seem to be getting very good at. So here's an example. This is again on my blog. This is an undergraduate from Yale, Sangir Azabayev. He has a system where you type in a statement in natural language, and the large language model outputs a statement in Lean, which is kind of cool. There's lots of examples on the blog post. So my final slide, just some conjectural future goals. Can we actually train these AIs to learn some algebraic geometry, or give them human written algebraic geometry and get them to translate the statements into Lean? Excuse me. Can these things translate statements of results in algebraic geometry, or indeed, right, like it's the last slide. Can we train an AI to do algebraic geometry? Can we make some kind of algebraic geometry chatbot where someone can come along and ask it a question? They're trying to read a paper, they don't understand what's going on. They can ask the chatbot about the paper, and they can attempt to put some kind of coherent argument together. This time it's going to be correct. So there's an idea. It doesn't have to be algebraic geometry. I just choose it because that's the thing that I tend to teach my graduate students. Can we build interactive textbooks? I think that's absolutely on the cards. There was a conference talk at a conference in UCLA last month where there's an amazing demo of that by Masso. So, you know, a textbook where if you don't understand something, you can click on it and get more and more of an explanation until you get down to the axioms of mathematics. Can we make Lean easier to use? Again, I think this is a possibility as we understand how mathematicians use it. And some completely crazy thing, I mean, can we prove Fermat's last theorem in Lean? I only asked that because my advisor proved Fermat's last theorem, and his advisor proved Fermat's last theorem. So why shouldn't I prove Fermat's last theorem? I think it should become a British tradition. It's going to take a while, but I don't see any real obstruction to doing it, and it would be kind of a cool project. So that's it. Thank you very much for listening. And here's an ad. Thank you.